Hello everyone, welcome back to the channel. So today we're going to look at vibration isolation under the topic of chapter 6, vibration control. So what is vibration isolation? Okay, it is a procedure which we want to reduce the effect of undesirable vibration. So how does it work? It involves the insertion of an isolator between the mass and the source of vibration. So there are two types of isolator. First one is passive isolator. The second one is active isolator, where passive isolator you don't need any external power, and active isolator you need external power. So a passive isolator consists of resilient members, which is stiffness, spring, and an energy dissipator, which is damper. So such as metal spring, cork, felt pneumatic spring, and also rubber spring. On the other hand, for active isolator, it comprises of servo mechanism with sensors in the processor and actuator. So there are two types of situation where we have fixed base and moving base. For the fixed base, we want to reduce the force transmitted to the foundation. And for the moving base, we want to reduce the force transmitted to the mass or the structure. So these are the type of isolator. So the first one is undamped spring mount, which is a passive isolator. Second is damped spring mount, which is also a passive isolator. Then the third one is pneumatic rubber mount, which is an active isolator. Because in order for the pneumatic to work, it needs an external power. So there are some introduction to the vibration isolation. So let's look on its fundamental. So for vibration isolation, we can categorize it into two categories, which is force transmissibility and displacement transmissibility, whereby the transmissibility ratio, denoted as TR, is equals to the ratio between Ft over Fo, which is force transmitted over the excitation force, while for the displacement transmissibility, the transmissibility ratio is equals to amplitude x over amplitude y, whereby the y is actually the amplitude displacement transmitted. So let's consider a case whereby we have two areas which is located next to each other, whereby on area 1 I have a pump with a mass m and it rotates on certain angular velocity, which is omega. And for the second area, I have a camera, okay, which is located on a table, and this area is located next to each other. So if let's say the pump is running, if the pump is running at a certain omega, okay, it will vibrate and force will be transmitted to the ground in area 1, and at the same time the camera will also vibrate due to the force transmitted on area 1. Okay, just imagine if you have a pump in one room and then a camera in a second room. So when the pump is running, this camera will vibrate. So if I draw the free body diagram, so this is for area 1, which is the pump, and this is area 2, which is for the camera. So let's say the pump have excitation force of Fo cos omega t. So due to this force, okay, when the pump is running, this force will be transmitted to the ground, and it will cause this camera to vibrate due to the amplitude transmitted from the ground to the camera. And this will cause the mass of the camera to move or vibrate in the x direction. So for force transmissibility, right, for this pump, we know that because it have excitation force here, therefore the equation of motion will be mx double dot plus cx dot plus kx is equals to the force, which is Fo cos omega t. So what happened to the ground? Okay, let's say this is the base of area 1. Okay, there will be a reaction force due to the spring here, which is Kx, and also due to the damping, which is Cx dot. So from here, you know that Kx is equals to Kxo cos omega t minus phi. Because we know that the general solution x is, if we assume general solution, x is x cos omega t minus phi. So for Cx dot is, so if I differentiate the general equation, that become minus omega x sine omega t minus phi. So if I put this general equation into this governing equation, okay, what I will get is that for the reaction due to the spring, it will be this, and the reaction force due to the damper will become minus c omega xo sine omega t minus phi. Therefore, from chapter 2, we know that force transmitted to the base, which is this one, force transmitted to the base would become square root of kx squared plus c omega x squared. Okay, actually the force transmitted is actually a product of resultant force from the spring and also from the damper. And if I factor the x, it will become ftx square root of k squared plus c omega squared. So this is the total force transmitted to the ground in area 1. So if I draw it back again, so basically this is, we have kx here and we have cx dot. So generally the force transmitted to the ground is actually Kx plus Cx dot. Okay, so how about the amplitude? Okay, we have learned it in chapter 2. So x is equals to force. In order for you to get the amplitude, here remember, amplitude from the force is actually k minus m omega squared plus c omega squared. Okay, you can refer this from the amplitude. Okay, this is the amplitude for force. If you forget, you can always refer to chapter 2 lecture notes. So since TR, okay, you need to be familiar with this TR. TR is actually the transmissibility ratio. So it is a ratio. It is a ratio either force transmitted over excitation force, or it's either displacement the ratio between the displacement amplitude to the excitation displacement. So we know that TR is for force transmissibility, TR is Ft over Fo. So I can write the equation as, okay, so this is the force transmitted and this is Fo. So if I put everything together, what I will get is that k squared plus c omega squared over square root of k minus m omega squared plus c omega squared. So what I did was I extract this Fo and I extract this Ft, put it together in the transmissibility equation, Ft over Fo, so I'll get this. And if I factor k from this equation, okay, what I will get is that we can also write it as 1 plus 2 zeta r squared over 1 minus r squared plus 2 zeta r squared. And we know that the zeta is actually c over cc, which is the damping ratio, and r is actually the frequency ratio, which is omega over omega n. And we know that omega n, the natural frequency, is the square root of k over m. So this is how do we get the transmissibility ratio. Okay. So if we refer to the plot of transmissibility ratio over R, you can refer to your page 16. So this is a plot whereby they plot the transmissibility ratio over the frequency ratio. So if you can see here, if the ratio is less than square root of omega 2, okay, this is the ratio. So if the ratio, frequency ratio, is less than square root 2 or 1.4142, what we will see that the transmissibility ratio will be over 1. Okay, so this is the region whereby the frequency ratio is less than square root 2. So if you can see here, the transmissibility ratio is more than 1. But if the frequency ratio is over square root 2, which is this region, so we can see that the transmissibility ratio is less than 1. Okay, so what we can summarize is that if we want to reduce the force transmitted to the base, therefore we need to ensure that the frequency ratio, or R, is over square root of 2. Alright, so if you want to reduce the force transmitted to the base, you must ensure that the frequency ratio is over square root of 2. So this is for force transmissibility. So the important part for force transmissibility is that you need to remember this. Alright, so moving on, let's look at the displacement transmissibility. So if I draw back free body diagram of area 2, okay, whereby we have a camera that's located on the table, and I can simplify it as something like this, where we have where the table have its stiffness and damping coefficient. So due to the force transmitted from area 1, it will produce amplitude of displacement. You can write it as YO cos omega t, and this is actually the amplitude transmitted from area 1, which is the pump, and due to the amplitude transmitted from area 1, this camera will move or will vibrate in the direction of x cos omega t minus v. So the mass will move, so this camera, the mass will move due to the amplitude transmitted from area 1. So if I draw the free body diagram, this, let's see, this is the camera. So due to the spring and also the damper, okay, the reaction would become kx minus y and c x dot minus y dot. So the equation of motion would become mx double dot plus c x dot minus y dot plus k x minus y, which is 0. So if I rearrange so that I put x term on the left side and y term on the right hand side, it will become mx double dot plus cx dot plus kx is equals to cy dot plus ky dot. So generally this is the force transmitted from the ground to the camera. So if you assume general equation, x equals to xo cos omega t minus phi, and x dot is minus omega xo sine omega t minus phi. This is for the x, and for y equals to yo cos omega t, and y dot equals to minus omega yo sine omega t. So if I put this general equation into the governing equation, which is this one, so I will end up with equation of negative m omega squared plus k squared plus c omega squared xo squared equals to yo squared k squared plus c omega squared. So in the previous slide, which is this one, we know that the transmissibility ratio is x over y. So we can write it as TR is x over y, which is in this case xo over yo, which is square root of k2 plus c omega squared over square root of k minus m omega squared plus c omega squared. So if I factorize k, I can also write the equation as 1 plus 2 zeta r squared over 1 minus r squared plus 2 zeta r squared. So it is the same. So basically the displacement transmissibility and the force transmissibility have the same equation for the transmissibility ratio, which is this one. Okay, so this is all that you need to remember. Therefore, I can write the equation of TR transmissibility ratio, which is x over yo, or I can also write it as force transmitted over excitation force, which is equals to square root of 1 minus 2 zeta r squared over 1 minus r squared plus 2 zeta r squared. So this is all that you need to remember for the vibration isolator. So to summarize, okay, let's say just now we have a pump And then let's say the omega is 50 radian per second, and this pump have a mass of 20 kg. So if I model it into the equivalent spring mass system, and draw it as like this. Okay, we have a spring and also a damper. So if I want to find the the spring coefficient, or if I want to find the damping coefficient, so that the force transmitted is less than the force generated by the pump, so let's say this pump, okay, know that the pump rotates at omega equals to 50 radian per second, and it have a mass of 20 kilogram, as I mentioned just now. Once this pump is activated, force will be transmitted. Okay, so if I want to find the K or C, okay, I want to find the spring coefficient or damping coefficient, so that this force transmitted is less than the force generated by the pump, which is just now, which is Fo cos omega t. Okay, so I need to make sure that the transmissibility ratio is less than 1 if the frequency ratio omega over omega n is over square root of 2. So as I mentioned just now, in order to get lower transmissibility ratio, okay, whereby the force transmitted is less than the force generated, so we need to ensure that the frequency ratio is larger than square root of 2 or 1.4142. Therefore, considering this case, okay, so omega n, we need to make sure that the omega n is less than 50 over square root of 2. Right, maybe you're confused. Okay, since we want to ensure that the r is larger than square root of 2, therefore the threshold, we know that r equals to omega over omega n. Since we want this to be larger than square root of 2, therefore in order to identify the k, omega n is equals to, therefore the omega n must be less than 50 over square root of 2, which is 35.3 radian per second. Okay, so this is for this case. So generally I know that the omega is 50 radian per second. So in order for me to ensure that the force transmitted is less than the force generated, okay, I need to ensure that the frequency ratio is larger than square root of 2. Therefore, to identify the k, we can get it from, we need to find the omega n first. So the threshold is 35.3. Okay, so this will result to r over square root of 2, and TR less than 1. So if the omega n is if omega n is less than 35.3, which is the threshold, so it will result to R, which is the frequency ratio, will be larger than square root of 2, and the transmissibility ratio will be less than 1. So let's say if I choose omega n equals to 20 radian per second. Okay, just now we need to remember that in order to get R larger than square root of 2, so I need to make sure that the omega n must be less than the threshold, which is 35.3. So 20 is less than 35.3. Okay, so this is less than 35.3. So if I calculate the R, so R is omega over omega n, which is the omega is 50 over the omega n is 20. Therefore, the R will be 2.5. So if I refer back from the plot here, so if R is 2.5, which will be in this region, we can see that the transmissibility ratio, the TR, is less than 1. Okay? And from here, we can also say that from this plot, in order to get the lowest transmissibility ratio for R larger than square root of 2, therefore I must choose lower zeta. If you can see here, okay, this is the region whereby, okay, just now we consider that the R is 2.5. So in order for me to get the lowest transmissibility ratio, if you can see here, if the zeta is 0, okay, we will get the lowest. If zeta is 0.25, we get here, and then if zeta is 0.5, we will get around here. So therefore, you can say that if there is no damper for R larger than square root of 2, therefore we will get the lowest transmissibility ratio. Alright, so that's all for this session. Next section, we're going to look at some example or some problems that we need to solve. Thank you very much.